Hi folks, Mr. Ackerman here. Thanks for watching. This is the supplementary video for Unit 3, Lesson 4, where we're going to talk about satellites and the orbits that they have around planets and whatnot, and also space stations and the idea of space travel, which may be coming to us in the future, hopefully sooner than we can imagine. Anyway, getting down to where we are in the unit schedule, let's just hop over to Adobe Reader here, scroll through the course pack, and get into the schedule. You'll see this is the last lesson before we have a review and our test. Everything that you need to know is in here, including practice problems, so make sure that you try those. Going into the lecture notes, I'm going to assume at this point you've watched my instructional video, and again you're going to notice the instructional video and the lecture notes here don't quite match up, so let's just go through them quickly so that you can experience what it would have been like if we were together in class. The first page of the lecture notes has a problem that you should be able to handle without any special instruction because we've done something like this in the previous lesson. You're given a situation where a natural satellite, a moon, in our case our moon, Earth's moon, whose name by the way is Luna, as in a lunar eclipse. So our moon is orbiting the Earth, and you're given a radius of the orbit, and you're asked a few questions about its speed and period. But there's a little hint at the bottom here that there's some information that you still need to solve the problem, and I'll leave it to you to figure out what that information is. And you can go look it up, it's no problem. Some people ask me during a test, would they be given that information? And the answer is yes. The information that you need here I will give you on a test. Although after you've done enough of these problems, you'll probably see that information enough times that you might actually start to memorize it, and that would be great. So moving along, let's get to the new stuff. You're going to see on the second page of the lecture notes, there's three little screenshots here. This first one comes from a YouTube video, the third one comes from a YouTube video, and the middle one is a PhET simulation. So what are these all about? Well, they're about circular satellite orbits and the implications that that will have for human beings who are engaged in space travel. So the first one is a video which if you hop over to YouTube and you just type in Tutor Vista Satellites, this instructional video will come up, and they talk a little bit about how satellites are launched and what the different kinds of satellite orbits are. And if you really want to get a feel for that after you've seen the video, go to PhET and download their simulation which deals with satellite orbits. Now I've got the older version on my computer, I'm going to show you that, but the newer version I'm sure is pretty similar. So let's hop into what that looks like, and I'm just going to move myself over a tiny bit there so you can see. What you're going to do here when you get into the simulation is click on the one that has the Earth and a satellite, just to keep things simple. We're going to imagine launching a satellite. And make sure you click on gravity force, velocity, and path. And when you do that, and you click play, you're going to see that the simulation is set up by default to create a circular orbit. So I'm going to pause that, and I'm going to move myself over a little bit more and click reset here, and you go back to the beginning. Now, here's where you can start experimenting. Click and drag the velocity vector a little bit shorter, but keep it in the same direction, and click play and watch what happens. The satellite crashes. It's kind of like if you were to stand up on a very tall mountain, and if you could take a ball and throw it, what path would it take? Well, it would take the same path that you just saw, and it would hit the ground, which is like a satellite crashing. So we're going to pause and click reset, and this time we're going to throw the ball a little bit faster, so I'm going to drag this velocity vector back a bit, not as much as I did in the previous simulation, and let's see what happens. And you notice this time it goes a little bit further, but it still crashes into the ground. And hopefully you're starting to get the idea here that if you could just throw this thing a little bit faster, maybe its curving would match the curving of the Earth's surface, and therefore it would never actually hit the ground. It would do what we call fall around the Earth, which is kind of a strange thought, but imagine a state of continuous falling where you never actually hit anything, even though there is a ground there. And here's what it looks like. Reset, play. You're falling, just like the ball that I threw in the first simulation, when it hit the ground was falling, only now you're going so fast horizontally that even as you fall, the ground curves away from you and you never actually hit it. So it's kind of like a competition between the curvature of the ground and the curvature of the orbit. And if they're the same, you get a nice circular orbit. But think about the astronauts who are on a satellite like this. Like, think of the International Space Station and our own Canadian astronaut, Chris Hadfield. I think he's retired now, but he was on the International Space Station. He was a commander for a long time. He felt, however you would feel on this thing, for hundreds of days. Now, what is that feeling? Well, if you think about it, it's the same feeling as free fall that you get if you go to Canada's Wonderland and you go on Drop Zone, or you take the first hill of a really steep, tall roller coaster. You know that feeling. It's a feeling of weightlessness. And so he actually felt the way you feel on that first hill of a roller coaster or Drop Zone. He felt it for hundreds of days, 24 hours a day, 7 days a week. And he got used to it. It was weightlessness. It's what you would feel if you were traveling through space and you were far, far, far away from any objects that could exert a substantial gravitational field, such as the surface of the Earth. Now, being in that situation is going to have certain effects on our health. So I'm going to pause this simulation, and we're going to jump into our next YouTube video, which is by a really, really cool YouTuber called Vsauce. I know a lot of you know who he is, but if you haven't seen his videos, they're really, really great. The one you want to look up is What If You Were Born in Space? And in this video, it's 13 minutes long, it's going to talk to you about the effects on the body of prolonged spells of weightlessness. And some of them are going to shock you, and they're going to make you really think, what would it be like if we actually went out into space to try to colonize other planets, or just to live out there for any extended period of time? And I think it's going to make you think twice about these wonderful stories we hear about how close we are to colonizing space. This is just my personal opinion, but I don't think we're anywhere near there. I don't know if we're going to see it in my lifetime, hopefully in your lifetime, but there's a lot of challenges to be overcome, and he's going to talk to you about some of them. Make sure you watch this video, very important. Getting back to the lecture notes now, and I'm going to move myself back into the frame here. So we're going to leave this page, and we're going to go to the next one, because as kind of depressing as the message I just gave you about space travel was, there is a ray of hope, which is that there's a way to make ourselves not feel weightless when we travel through space. There's a wonderful movie from the late 1960s by the great director Stanley Kubrick. It's called 2001: A Space Odyssey. And if you've never seen it before, I'll warn you, it's not like a sci-fi thriller in the, shoot 'em up, aliens attacking way, but it is a kind of cerebral movie with a lot of deep thoughts in it, and it raises questions about the origin of life on Earth and all that stuff. Very cool. If you've got the patience to watch it. I think it's about 3 hours long. Watch it. But the thing I want to point out to you is that the science in it is really bang on, and considering this was close to 50 years ago, they did an amazing job. There's 2 videos I want you to look up on YouTube. One says Virtual Discovery Centrifuge, which is a clip taken from that movie, and the other is 2001 ASO, A Space Odyssey, Centrifuge Spin, which is also a clip taken from there. If we jump into YouTube, you're going to see these here and here. And what I want to show you is this really cool idea for how a spaceship might operate in the future to create the feeling of gravity, so that actually the things that Vsauce mentions in his video are not going to be as much of an issue in terms of their negative effects on our health. So let's check it out. In this space station, or this spaceship, you'll see in this scene, the space station, or the spaceship, is actually rotating, and it looks like you would be sitting on almost like the outer edge of a spinning tire, if you can imagine that. Or if you've ever been to Wonderland, there's a ride that kind of spins around and it throws you outward against the outer walls. Of course, that's the fictitious force. I think the ride is called Nightmares, and let me see if I can find it here. just so you know. So let's go to videos, and here it is. There we go. Just watch this video. Have you ever been on this one? It's a great ride. It's not that thrilling in that it twists and turns or anything, but it just spins and everyone stands up and it goes faster and faster, and eventually you're pinned against the outer wall. Your back is pinned as it puts you into a vertical circle, and soon it's really interesting. The people at the top, they think they're going to fall down to the ground, but they don't, because the centrifugal force that you learned about in lesson 2 is pushing you outward. And of course, the people at the bottom, they must think they're going to slam down into the ground, but they don't, because the normal force is pushing them upward, and they continue in a circle. So the idea is this. Instead of having your back against the ground here, put your feet there. So you see how the chairs are, and you see what this looks like. People would literally walk around in a circle, going around and working inside the space station. And if you spin it at just the right rate, you get the feeling of Earth gravity. There must be some rate you can spin it at so that the centrifugal force pushing you outward equals the normal force, and you feel like you're in equilibrium in that frame of reference. Let's see what it would look like if you were actually in the space station. Would you feel like you were spinning around? Would you get nauseous? Well, here's a scene showing that actually, no, you wouldn't. So the actor here, who's one of the astronauts, he comes out from another part of the ship and he climbs down a ladder, down as in radially outward toward the floor. And now he can actually go and he can walk to another part of the spaceship. And because you're in the frame of reference, you don't have that spinning sensation. He just feels like he's on Earth, only it's a weird Earth. He's in a room that's kind of curved, and he can look up and see the floor, which is actually the ceiling on the other side, if you can imagine. Anyway, great movie, scientifically very well done. The story itself, the drama, exceptional. Check it out. It's worth your time. Getting back to our lecture notes, so what I'm going to ask you to do next is to try a practice problem that's in the textbook. It's number 10 on 150, and it actually shows a drawing of that guy, basically, inside the space station, which is spinning, and they ask you, you're on a cylindrical spacecraft, you're traveling to Mars, here's the size of the space station. We want to spin this thing at a rate that gives the astronauts the feeling like they're in Earth gravity, like they have their earthbound weight. Give this one a try. Draw free body diagrams in the Earth frame of reference. So this would be the inertial frame of reference, as if you were viewing the space station from without, and then draw it when you are inside the space station. So the free body diagram from within. And see if you can solve for the rotational frequency, the rotational period, the speed that you'd be going around in a circle for a space station of this size. And that's it for now. Thanks for watching. I hope this gets your imagination going about what it might be like to travel through space, and I hope that one day we do colonize space. And until then, I'll talk to you later. Bye for now.